Right. How's it going? Sorry for being a few minutes late. Apologize for that. So what we were talking about last time? Anybody remembers what we were talking about last time? Like distributed transaction management, right? We talked about centralized two-phase blocking and distributed two-phase blocking. We've noticed that the only difference between centralized two-phase blocking and distributed two-phase blocking is in the lock manager. So the lock manager is distributed in the distributed two-phase blocking. And that made it way easier and removed a lot of overhead, a lot of bottleneck. So because in the centralized two-phase blocking, you have to go through the transaction manager that has to make sure that the centralized block manager grants or release locks, right? But if you have distributed block manager, you don't have to do that, right? So this will make will lead to less messages transmitted across the cluster, especially if you have a lot of transactions and you have a lot of operations in each transaction. So this is basically what we discussed last time. We discussed also timestamp ordering, right? And the timestamp ordering approach, all what it does is basically, instead of using a lock to achieve serializability, you use the timestamp. And the timestamp is no more than just unique, monotonically increasing numeric value that represents. You can use a clock to actually present the timestamp, but this clock has to be shared across all transactions and all participants in the system. All right, so and we've seen the initial version of timestamp ordering, TO, and then we move to what else? Conservative. A more conservative version is called conservative TO. And in conservative TO, basically instead of taking an action, and an action here means whether to accept or reject the operation of the transaction immediately, you actually, in a conservative timestamp ordering technique, you wait a little bit to ensure that this transaction will not restart. Because in the basic version of timestamp ordering, we have to restart. If we reject the operation, we have to restart this whole transaction. So to avoid this many restarts, especially if we have a lot of conflicts in the system, conservative TO can be more efficient. However, if you go extreme conservative, you're going to have a serial schedule. And again, you defeat the purpose of concurrency and transactions and all these kind of things if you have a serial schedule. So you don't want to also run into that. So you have to come in and come up with a sweet spot. There's also another version of the timestamp ordering called the multi-version timestamp ordering. Multi-version timestamp ordering is same as timestamp ordering, except that whenever you write a value, you don't write it on the data item location. You write it in a different location. It's a multi-version. You have multiple versions of the same data item. Okay? And each version for sure has a timestamp also. So what's the benefit of having multiple versions? Because this way you're not going to restart, right? It depends on how many versions you have. So you can always write a new version. But there are still limitations to achieve serializability. Limitations comes from the fact that you don't read, the version that you choose to read should be a version that has been written by an older transaction, right? So you're going to have multiple versions of the same value, but you need to choose the version that will not cause any conflict. The same for the writing. So you need to write, writing, you're going to write a new version anyway, okay? So let's assume you're going to write a new version, it's fine. But reading is the issue here now. So this is why you have to make sure that the version you read does not cause any conflict. And a conflict always happens when you read something that has been written by a younger transaction, right? So if a younger transaction has access to this item and an older transaction needs to read it, what does it mean? This means that you need to restart. Why? Because remember the original problems we talked about, the conflicts? You might actually, the older transaction might have read the value, and then it might be reading a totally different value for the same exact data item if a younger transaction wrote into it. So that is a conflict, and we need to make sure that doesn't happen. So this is just another way of doing the timestamp ordering, which is a multi-version timestamp ordering. All right, so in concurrency control in general, we have talked about two main mechanisms. One of them is two-phase locking. It's a locking-based mechanism. And the other one is timestamp ordering and its variants. And this is basically using timestamp, and based on the timestamp you decide whether to do the action or to start the transaction, whatever it is. If you look up a little bit more, usually there are two ways to do concurrency control. Think about the purpose of why we do concurrency control in the first place. We have all this transaction management, a concurrency control mechanism, two-phase locking, timestamp ordering. It's that we always doing that because we want to avoid conflicts. We want to make sure we don't have conflicts, and hence we have a consistent database, right? We achieve consistency. But all the techniques we have seen, two-phase locking or timestamp ordering we have seen so far, they're very pessimistic. What do I mean by this? Pessimistic means, it's actually self-explanatory, but from that perspective is, these mechanisms always presume that there is an issue that's going to happen. And I'm taking all my precautions early on so that nothing happens, right? So when you did two-phase locking, whenever I'm writing into something, exclusive lock, right? Why? Because if I don't do that, some issue might happen. And it might, for sure. Something can happen. But doing the locking that way is very pessimistic, because like you're always assuming the wrong. You're always assuming the worst. Okay? So it's pessimistic concurrency control. So in the pessimistic concurrency control, if you want to generalize the framework, so you have four main phases when it comes to concurrency control. The first one is validate. The second phase is rate. Third phase can be compute. And the last phase is rate. What do we mean by this? This is a timeline. What does validate means? Validate means you have in the locking, for example, you have the lock manager. You go ask the lock manager, can I get a lock or not? on this item because I want to exclusively lock it, or I want just to read it, but I still want to lock on. So you validate whether this operation can be done or not through the locking or even through the timestamp. You also check the timestamp. I mean, should I do this or should I restart? Should I reject and restart? So this is a validation step. And then you read the value that you want to read. You might do some computation, which is the logic in the transaction on this data item. And then you write. Okay? These are the possible states you go through. Putting the validation early on, this is why it's pessimistic. That's the bottleneck here. So the validation step, you always, before you do anything, you validate. Granted, it can achieve the serializability and it's efficient in that sense. It can make the data very consistent. But again, it has issues because what if you have a lot of conflicts in the database? Or not like this, what if you don't have a lot of conflicts in the database? Why do the locks, right? Locks might not be necessary, but it's still going to do it because it assumes the worst, right? So if you want to be optimistic, where do you think I should place the validate step?
Before write.
Before write, exactly. So first of all, we all agree that we need to validate at some point because otherwise it's going to be a disaster to the database. So, but like you guys mentioned, I can move this all the way before the write. Why? Because write is the time that you have an issue. So I will validate. But what does that mean? It means that everything before the validation could have issues. So I can do a lot of things. And I might, while doing all of this, I might have done a lot of disasters, right? But as long as I didn't write it, it's okay. So I do a validation step before the writing to make sure whether anything I've done is a disaster or no. If it's not, good, move on. If it is, take some action. Taking an action in that sense means sometimes you can redo some of the steps that you've done. So it's like, dude, you've been so optimistic and we have a lot of conflicts in the database, so probably you should go back. Or you're good, no disaster, you moved, and everything worked, and you're consistent. So let's write them. So it's a very, like as you can see, very slight difference in the workflow, but it made a huge difference. And both of them will get you to the same place in terms of consistency, but it's how you think about it. So, pessimistic. When do you think pessimistic would be good? Being pessimistic? What's that? Lots of conflicts, exactly. So if everything is just it's a disaster in the database, there's a lot of conflicts. So being pessimistic is good, right? Because you see, even in life, right? So you see everything bad, so you need to pay attention when you're walking, right? Because you might fall. So an optimistic on the other side is good when you don't have a lot of conflicts. Why? I mean, life is good. I mean, why do I have to take precautions? All right? So these are two, again, looking from a very general perspective. Concurrency control, these are two main schemes that you guys might think of. But this is from a workload perspective, when we have a lot of conflicts or no conflicts. What about from an implementation perspective? Which one is easier?
The pessimistic.
Who thinks it's a pessimistic is easier to implement? Who thinks the optimistic is easier to implement? Who doesn't care? So there are some people that didn't answer yes to any of the 3 questions, right? It drives me crazy, okay? All right, so it is actually the pessimistic is easier to implement. And the reason behind this is that you just have a lock manager. The lock manager takes care of everything. It tells you, you remember this table that we wrote about like shared lock, exclusive lock? Very simple, right? It's nothing. The lock manager will check it and give you an exclusive lock. And once you have an exclusive lock, you can do whatever you want to do. This two-phase locking, for instance, you release locks at the end of the transaction, do whatever you want to do with this item. It's way easier. While in the optimistic, yeah, I mean, you can do whatever you want to do at the beginning, but when it comes to the validation step, it's hell. Because if there are conflicts, resolving the conflict is actually a difficult task. So implementing the optimistic is very challenging. This is why most database systems don't implement the optimistic approach, right? Why? Because people that develop database systems initially said, let's go with the easy way, right? So talking about Postgres, for instance, it's locking based. It's a pessimistic locking based because there are locking based mechanisms that are optimistic, okay? But it's a pessimistic approach. So people usually, this gives you an idea of like if you're building a system, people that build software systems, sometimes they take decisions not based on the performance or based on anything, just based on usability and simplicity. And this applies to so many things, not only the database systems, operating systems, like a lot of the operating systems that we are using these days, there's a lot of issues with it. But as long as it's working, it's fine, people are okay, so we're good. Networking systems. Like I always like when I go to networking conferences, like the brightest minds, in the networking theory and all these kind of things, thinks this internet is the worst thing ever, right? From a networking perspective, right? So they think it's the worst network ever. People who build it don't know what they're talking about. That's what they think. Why? Theoretically speaking, it's true, but it's working, right? And that was the easiest way to do it, so we did it, and it's still working till today, right? It's working for you guys, right? Yeah. It used to be really bad in the past, by the way. So, okay, this is a side conversation, but you guys know initially that all the addresses in the internet, like all the IP addresses and all these kind of things, it was managed by 2 people, manually. So that was like in the 90s, like late 90s even. So everything was manually managed by 2 people till they figure, man, it's getting too large. Let's just figure out a way to automatically do that. And now they do it, finally. Anyway, so it just gives you an idea how things, even those things that are really impressive and really made an impact in the world, maybe they were not built in the most neat, like the neatest way ever, right? But they're still good. Anyway, before I move on, I received some questions by some of you asked about, there is, in the syllabus, there is a book. I'm not using it as a textbook, but it's as a reference. And so far, what are the chapters that if they want to read further, they can read from? So before we move forward with the content, I'm just going to tell you what chapters we have covered so far. So in the book that is in the syllabus, the reference, we've covered topics from chapter 3. This is fragmentation. Okay? You guys remember fragmentation, right? I'm glad. Good. Thank you. Yeah. And we covered topics from query processing and optimization. And that was chapter 6, 7, and 8. And we covered also topics from concurrency control, right? We were just talking about that now. And that's mostly chapter 10 and 11, okay? So this is just to, if somebody wants to read more, that's fine. But again, the slides and what I say in the lecture is enough, okay? Is enough for the exam, for example, or, but you guys more than welcome to read this book or other books as well. There's also other content that I get from other books, and there's some content that I personally put in the slides, right? So I'm just saying this is the reference that I mostly use. So if you want to take a look at it and read it, please feel free, and we can discuss it even, right? All right. So we're continuing the concurrency control, and we talked about the concurrency control and locking mechanism and how can you do concurrency control. What if you have deadlocks? 2 classes back, we talked about deadlocks in traditional database system. In a distributed database system, how can you deal with deadlocks? First off, do you guys remember what did we do with deadlocks in traditional databases? That was a week ago we talked about this. What did we do? Just quick. Yeah, how did we detect it? Wait for a graph, right? So we had a graph that has all the transactions, and if the transaction is waiting on the other, there's an edge. And if there's a cycle, there is a deadlock, you need to break that cycle. So you can restart one of the transactions, like break it and like end it and restart it. Okay, good. This is good technique. So how can you do that in a distributed database system? So you have distributed sites. So different sites, and each site has its own data processors and log manager and all these kind of things. So how can you build the wait for graph? A straightforward approach would be to have a central location where you collect the wait for graphs and in a central location, right? And then take a decision at this location. What does that mean? So you build transaction originate, right? At one site. And this transaction do locking and all over many operations. So what you need to do basically is that each site will build its own wait for graph. And the wait for graph is similar to the one we talked about before. So you have multiple sites. So site 1, S2, and then Sn. And you have a wait for graph here. Okay, 1, and wait for graph 2, and wait for graph N. So you have multiple sites. So you keep building the local. And then every once in a while, every site will send us to a central location here. And this site will basically combine all wait for graphs together and then look for cycles. And if there is a cycle, that means there is deadlock and deal with it. Now you detected the deadlock, you can deal with it. Do you guys think that will work? Anybody thinks that will work? It will work. Okay, I'm telling you, it will work correctly. It will find deadlocks. But it has issues. What are the issues? Any ideas?
Too much time for aggregation.
Too much time for aggregation. Okay, that's it. That makes sense. What else?
Data is not consistent because site 1, site 2, the time go to the center point is not the same.
Oh, I get your point. So you mean like you have, everybody sends it at different times?
Yes.
Let's assume that we all stop at one point, central location stops, and we all send a snapshot of what we have at this time. So what about the communication overhead? You have a lot of communication overhead, right? Especially if you have a lot of transactions and you have a lot of wait-for graphs and things are changing over time, dynamically evolving very fast. So you have to detect it early, you have to send these local wait-for graphs all the time to the central location, right? And if you don't, the deadlocks will happen for so long and it will affect the performance, the throughput of the system. Make sense? So you either have a huge communication overhead, or you run into the problem of having a low throughput if you don't submit it on a frequent, like on a regular basis. Makes sense, right? So how can we fix that? Please.
Instead of sending the entire graph, why don't we send just the control segments for each specific block?
Instead of sending the
entire graph,
entire wait-for graph,
yeah, we should just send the control segments. For example, if some block is being used on cycle, then just send it to that I blocked it at this point of time and I unblocked it after this is closed.
good idea. Yeah. So John in the back, what he's saying here is that why do I need to one site to detect deadlocks, right? So why don't I distribute the deadlock detection across multiple sites? This will work fine if the deadlock is coming from the local site, which means that all the transactions, all the edges that cause the deadlocks are local. So it will be the same, it's okay, right? So it will be the same as a centralized database system if all the edges are local in that wait-for graph. So I will just build the wait-for graph, and then if there is any cycle in my local wait-for graph, I will deal with it. But sometimes the edge spans multiple sites, right? And the cycle can span multiple sites, not just 2 sites. So the edge 2 sites, but to get the cycle, you figure it might actually go through 10 sites to actually figure out that there is a cycle. So in that sense, you don't, even though you're, in that sense, if you just test for local, you cannot just easily test for local wait-for graphs. This means you have to send signals to the other wait-for graphs. So if you have an external edge, you have to send this edge to, or probably potential cycles, to the other site. And if you send a potential cycle to the other site will take the puzzle like that you have and connect it together and will look, yes, now I have a cycle. Let's deal with it. But if I don't, might send also some information if there's a potential cycle to another site, and so on and so forth. So in that case, you don't have one central site to take care of the global deadlock detection. You can do this locally, and if anything needed between sites, you just share information between sites. Send signals. And again, put everything together to have a better understanding of the wait-for graph, the bigger wait-for graph. But no one site at one time have a global view of the whole wait-for graph of the whole system. And this is how it's done in history. Easy, right? So this is basically how you do deadlock detection for using wait-for graphs in distributed database systems. Any questions? Please.
So the sites never actually interact with each other, right? There is always that central component
No, they interact with each other.
They interact.
Yeah. So they interact with each other, they send signals to each other, right? Please.
So out of 10, say 3 have shared their information with each other. So how would we decide master and slave between them? Like,
There's no master slave, it's distributed. It's distributed and not necessarily in a master slave kind of approach.
Like who would decide which transaction to actually like give up, like 3, or because 3 are at the same level, so who actually would decide which T1 or T2 should we give up to make the
This decision is basically based on, let's assume one local wave graph in one site. It's testing for, it's looking for cycles. If it figures that there is a potential cycle through an external edge, it will voluntarily send this this potential cycle elements that it has to the site that it thinks might have a potential cycling. Okay, so in this case, they're all equal. Okay. It's more of a collaboration kind of, and if there is no need, you just do things locally, right? This is just done if there is a potential cycle. All right. So let's move on. What kind of music is that? No, seriously, what is it? What? Replicated data management. Okay. So we're going to switch gears. We're going to talk about replicated data management. We received a lot of questions. So far, when we were talking about concurrency control and a lot of the topics we talked about in distributed database systems, we didn't talk much about how data is replicated. And just initially, when we talked about fragmentation and localization or locating the replicas and the fragments, we just briefly talked about it. So we mentioned, I believe, maybe a couple of weeks ago, that the main benefit of replication is availability. And I give you an example of Facebook and all, right? Yeah. So that's the main benefit of replication. There are other benefits we discussed for sure. So if you have availability, you can have more scalability. And if you have replication, if you replicate parts of the data across sites that are geo-distributed, you can actually get better performance because you get the data closer to where it's accessed. Right? So replication has all these benefits, and the main benefit again is availability. So what is the issue we discussed? When you have updates. Why? Because how can you update multiple replicas of the same item? So if you don't have updates at all, replication, yeah, you have availability and you can read multiple versions at the same time because we don't update it, so it's the same all the time. But if you have updates, now things will become problematic. So which version should I read? Would I have multiple transactions? Which transaction read which version? We need to make sure everything's consistent, so they should be reading the same exact thing. They're not reading two different things. So how can we take into account all these issues? Let me ask you, let's start with a very simple way to do that. So transaction generally so you have a value, a data item. This data item is called X. But this is the logical data item. So logical view. So for the user sees X. But in fact, if you have a replicated data, this x is not just physically, it's not just x, it is, let's assume it's replicated 3 times x1, x2, x3. Right? So, yeah, for the user it's x, but from a system perspective it's actually 3. So in that sense, so how, whenever I have a transaction that reads or write into x, how can I do that? So when I'm writing x, that's also a user operation. The user thinks that x value should be this new value. So if I just go and write x1, yeah, I've written x1, but that doesn't mean that I've performed this operation. To say that I performed this operation, what should I do? I have to write to all of them, right? And this way, I've written to all of them. What if I'm reading? I'll read one of them, it's okay. Because it's the same. So the very initial, the very simple way to do that is to assume that every single replica, every single operation that runs, whenever I'm doing a write x, the user asks, for example, for an exclusive lock on x. When the user asks for an exclusive lock on x, I will go ahead as a system and lock x1. So exclusive lock of x, it means let's call it write lock of x, right? So it means a write lock on x1, a write lock on x2, and a write lock on x3 at the same time. And then when you do the writing, you have to maintain the lock on x1, x2, and x3, and then go ahead and do y, write x1, write x2, write x3. And you're still having the exclusive lock on all of them. And then when the transaction ends, what happens? You release the locks, right? On all of them. This way, you ensure the database is consistent, right? Because, yeah, you apply the locking, two-phase locking, you assume that each replica has its own, you have to make sure that it's locked. So you achieved consistency. But what is the problem with this? If there is a problem. And again, whenever you read, you can read any value of them because they're all the same. Yeah, please.
We need to keep the location where x1, x2, x3 are.
Keep track of the location. Okay, before we do that, I just forgot to mention something. So for the write, you need to have a write lock on all the replicas and then do the write. Okay? For the read, you read any version, but you need to obtain a shared lock on all of them. Don't you agree? Because if you don't obtain a shared lock, what's going to happen? One of them another transaction might modify. So a shared lock, you have to obtain a shared lock on all of them and then read any one of them. So this mechanism again achieves consistency, but it has an issue. What is that issue? First of all, it's correct to achieve consistency, but
you can update it offline. Like if some other application is having a read log on some site, for example, some other application is having a read log on x2. You will not get write lock on x2, right? That means write lock on x will fail. In the meanwhile, you can update the x on the other two locations and.
No, I mean, like, what is the issue of this?
Really expensive.
Why is that? Who's talking? Yeah. Please. Hey, why is it expensive?
Because have to update the law, maintain the law, read, write it, and then have to simultaneously read it.
So it's very expensive. Okay, so it's very expensive because you do a lot of blocks on a lot of data items, right? Okay, that's true. So it is very, locking one item is not the same as locking 3 items. And writing one item is not the same as writing 3 items. So it is more computationally, more time consuming than the traditional one. But I have to do it, right? Because otherwise I don't have consistency. That's a good point. So it is more expensive. Makes sense. What is another problem? Please.
I think the main purpose of availability won't be solved because our main purpose for replication was that if one user is using it, so the other users can use it. So one user is performing the right operation. Other users can't do it because the right block is going to all be replicated.
Good point. So what she's saying here is that even though it somehow in some situations it defeats the purpose of availability, and that was the main purpose of replication. So the reason behind this is you do lock all of them at the same time. If you have one write, this means you cannot read anything. And if you have one read, you cannot write anything. So it's just like you blocked everything. And most importantly, not only that it causes this, it even introduced a new problem that will make the system less available. Anybody can spot that. Let me give you a clue. What if the site that has X2 went down? What's going to happen? Cannot do anything, right? Totally. Why? Because the logic that I have, I cannot proceed unless I have a lock on every single one of them, right? Unless I write all of them, unless I read one of them, it's fine. But unless I write one of them, all of them. So if site 2 is down, you're blocked. You cannot do anything. The transaction, that means the transaction is blocked. That means that more transactions can be blocked, and that means the system will not be available, right? So it actually introduced a problem. So this is why, I mean, when you think about replication, if you think about this straightforward, naive approach, no. It's like, yes, we could have done it, but people usually don't do that because it's more problematic than it is solving the availability problem. So there are several ways to do with them. So if you move, let's move away from the basic thinking a little bit and see what we can do more. So what, there are, what if I just lock one copy of these kind of replicated lines? What's going to happen? So in other words, that the readers will lock and access a single copy, and the writers will lock and update all copies. What's going to happen in that sense? So readers will lock and access a single copy, and writers will lock all copies and write all copies. So will this achieve serializability? Consistency? It will, right? Totally achieve consistency. What is the problem with that? So readers read and access a single copy, and writers write and lock and write all copies. Please.
that site moved now, where the read block is there. So like writers would say that all the sites they want.
We will elect another site to be the primary site for the read if there's one is down. So that's problem. I will solve it for you that way.
Too many users are accessing the site, then too much traffic might actually slow down the end access.
When what?
Too many users, if they are accessing the site, it might slow down the end access.
If there are too many users accessing the site, accessing in what sense? Read or write?
Read.
If too many of them are accessing the read, you don't have much availability, right? Because you have to read, lock and read one site. But the idea of read and lock one site will give you more flexibility, right? In another sense. So yes, you're right. So I lost the availability of the read sometimes, okay? But I still got some benefit because I don't need to, if I have a shared lock and I have a shared lock on all of them, this will lead to no writes at all, right? Writes, I'm forced to do it to lock all the copies because otherwise I cannot achieve consistency, okay? So this is not a solution. I'm just giving you like one step ahead. What can we do? All right. So, in other words, what have I explained to you? Is it good for read availability or for write availability? Good for read availability, right? And it's poor availability for writes, right? All right. So now, I just want to draw this. How can we solve the problem? Is there any other schema you guys think of can solve this problem? What can we do with the sites if we have replicated data? So you have, again, x1, you have x2, you have x3. So if I want to read or write, I want to listen to your ideas. How can we do that? In a different way. There are limited ways anyway, right? So just I want to listen to your ideas. What do you guys think? Please.
Maybe we can maintain the versions of different versions of read. I mean, if there is a write, then we can update the version of write, and then we can update the older copies of all the different sites.
So reads, what we're going to do with the reads? We're going to do the same, right?
So read is accessible every time. So whenever you are reading, you are locking only one site, and there might be a concurrent write on any other site. And whenever that update happens, then after the read lock, shared lock is removed from the site from where I was reading, then you can update that site from the site.
So let me see if this is the thing. So for the reads, you select a primary site, okay? The primary site, you lock and read from that site. For the writes, you select, also you have one primary site, so you lock that site, but you write to all the other sites, this site and the other sites. What does that mean? If you have a primary site that you do the locking on, and you read and write from this site, while you have multiple, the other versions you write into them without lock, what's going to happen? You have more write availability that way, right? Because you don't lock the other sites and you just write, you directly write into them. You only lock one site for read, and you only lock this primary site for writes, while updating all the copies without locking. will this achieve consistency or not? It will, because you're reading from the primary site that you lock. Alright? So it will achieve consistency, but still suffers, it does not achieve full availability. It gives you higher write availability. Okay? Please.
If there are writes being done on two different sites by two different people, then again it's inconsistent.
The write is on a primary site. You lock and write, like you lock a primary site, and you write on this site, and then you write on the other sites as well. So all the writes will happen, the lock will happen on the primary site. So, in other words, what does this mean? You're right about something, by the way. That means that, yes, I have consistency, so whenever I'm writing something, this primary site is consistent, and I'm reading and writing to it. But I'm also writing things that are in other sites without locking. What does it mean? It means that I can have multiple versions, right, on these sites. So that means that I have at some point to resolve that at these sites. Get the last version at these sites. But it's not going to cause me any problem. I can do it at any time as a system, because from a user perspective, the database is consistent. I'm having more write availability, and the system is consistent. I can keep writing. The user sees the consistent value. And the sites that get so many writes, I will just get it, like fix this later. So the idea is that you lock the write, update the primary site, and then commit. Okay? But part of the commit is to propagate the writes to the other replicas as well. But from a user perspective, since the user will read the primary site, it's consistent. And the commit from a system perspective means that I have to make sure that I propagate these values to the other sites. So please.
If we read and write on the same primary site,
Yes.
it will be the same as a synchronized system.
No. Oh,
Wow.
partly. No, there's still replicas and you're still writing in the replicas. It's not the same.
But the user can't read the replications. We must read the primary
But
site.
you can write the replication.
Read.
You might write in the replicas. And another transaction, like this primary site changes over time. So you still get some sort of availability, but not full availability. You're right. So the general question here is that, isn't it this similar to a centralized system? And the answer to this is no, mostly, but partly yes in some sense. Why? Because we have a primary site. So this primary site limits the availability for sure. But is it similar as, no, it's not similar, because I still have replicas and I still update these replicas. And if the primary site went down, I can choose another site to go up and I have more availability this way because the data is replicated. So I have some availability, but not 100% availability. You're right. Please.
Yes, so like when there's an update in the primary site and simultaneously on the other replicants there is a read. So what if there is a conflict, like the update doesn't happen in the replicants, but you are still reading?
It's alright. Here's what happens. So let me tell you, the primary site, here's what you do. Let's assume X1 is the primary site. Okay, and you have a write operation. What you do is you lock. Okay, X1. You're not locking X2 or X3. You're locking X1. you write x1. Not only this, you do a local commit on x1. But part of the commit logic is something called, once you say commit, you have to store this in the logs that this has committed. And this committed means that I need to propagate. I'm not in a hurry, but I'm going to propagate this value to either x1, x2, and x3. So this propagation doesn't happen immediately. You can actually commit the transaction, commit it here locally, and this way you commit it fast, because if you wait to log and write 3 things, that takes a lot of time. So you committed the transaction fast, okay? And when you committed the transaction fast, this means you increase the throughput of the system. So that's one thing you get. You get more availability even that way with increasing throughput. The other replicas, I guarantee that they will get the value that they need, but this value will be delayed. I'll propagate this value later. Why? Because I have a primary site and I'm making sure that this primary site is consistent. That's what matters to me. So in this case, you have replicated data. However, you have a primary site that you lock for reads and writes and read from. So even though you have replicas, you still commit it locally. You still get the same performance you want, right? And again, this is just to clarify, this is just how to deal with replicas. But this can be running in a distributed concurrency control mechanism that we discussed and all, distributed deadline detection, everything. Okay? So this propagation happens later because it's okay if these values are not up to date. So the gentleman in the back mentioned that that means that you can get multiple values of x2 and x3, I mean, because you didn't update it immediately, you didn't lock it, and you didn't update it immediately. Yes, this will happen, but after the commit, this propagation have a sequence number, and this sequence number will be resolved once you want to update the value of x2. And the good thing about this is that you have the replicas, you update them, and if you have the primary site goes down, you have a guarantee that these values will be updated also, and you can elect one of them to be the primary site. All right? All right. Oh, please.
I have a question. So the updates to the replicas are not spontaneous. They might happen after a particular time.
The updates on the replica might happen after propagated. Yeah.
So
they're not updated at the same time as the primary site.
They might have jobs maybe say after 5 minutes or something like that. Something like that.
Yes.
So what if the node goes down, then the database would be consistent in that case?
The database will be consistent because the primary site is the site we read from.
But what if the primary is down and we select some other node as primary, but the updates have not been propagated yet? So is that handled somewhere?
Yeah, but there is a log. The log will make sure that this will make it to x2 and x3. This problem is the same with, this is a separate problem, how to do logging. This is a separate problem. Because this will happen, let's assume you still have using the original when you do the locking on all of them, right? And things, before you write in the third copy that you locked, things went down. What's going to happen? There is a recovery module, right? So this recovery will make sure that everything will be brought back to the consistent state. Please. Somebody was here first, I'm sorry. Same question. Okay. So, please.
Yeah. So in this case, the primary state must have all the data. Otherwise, if you can.
It has. We're talking about. I'm sorry. Just let me clarify this. We're talking about just one data item now.
Yeah. Just one
Well,
data.
one data item.
Yeah, because but if you want to read something, you must read everything from the primary. Otherwise,
No, you can have multiple primary sites for different fragments. You can do that. That's also the benefit of having a distributed system.
oh,
Like you can say, okay, this is a primary site for definitely not only X1, but for this part of the data. Okay, but this part of the data is replicated, and the same goes on the other side, you know? So that's also the benefit of having a distributed, replicated data system,
oh, yeah.
right? But I know we're focusing on X1 here is just a single data item. And all this trouble we're going through is just how to make sure this is, we make this data item consistent.
But if you want to, you try to read some data that is not in primary.
It's okay. I mean, the data could be anywhere, right?
But you want you try to.
You might have multiple primary sites for different parts of the database. That's what I'm saying.
Oh,
Okay. And secondary sites will be the replicas, right? Other question? No, I mean, behind you. She was first. Yeah, please. Yeah.
Or something else.
You.
So when you said that
Please don't. Yeah, go ahead.
so first we make X1 as a primary site and then we lock it. So that means that when we are locking it, so if there is any read request, you won't be able to read from it, right?
Read from X1.
Read from X1.
Yes,
or,
we cannot.
Or in general, if there is a read request, will we be able to read from X2 or X3?
In that's
In that
no.
case, no, right?
No.
So that means so what is the use of X1 and X3? I mean, like we are just locking X1.
No, there is a use for it. I told you, I just said that. I just said let's assume one site is down, we have the data replicated.
But what if the site is not done? What we just want availability, like two users are
That's a different scheme. I understand what you're talking about. I'm just explaining different ways of having replicated data. Okay, let me explain this also because maybe I confused you guys. Availability means different things, right? So yes, if I have no writes at all, and I have multiple versions of the same data item, X1, X2, X3, I can achieve high availability in that sense that I can direct 10 users for X1, 10 users for X2, 10 users for X3. But that's not the only way you achieve availability. Also, availability means that if you have one site down, you have the data in another site and it can take the same tasks, you know? And that can achieve this because you have replicated data and you make sure if the updates are propagated there. And if you have, as we were talking about here, the primary site does not need to be centralized for the whole database. You can have a primary site for part of the database, like I'm talking primary site for this table, a primary site for the other table, a primary site for this fragment, another primary site for a different fragment, you know. So in this case, it's not just, how can I say that? It's not like just a rigid thing, it's still distributed. Make sense? Yeah. Or you can do the, instead of having this local commit that we did here, another way to do it is lock X1, right? And then you write X1, also here, the primary site. And then you propagate the new value. Make sense? And then you, instead of doing this kind of local commit, you have a distributed commit approach. And the distributed commit, even though you didn't lock X2 and X3, but you received a signal from them that yes, I mean, I got the propagated value. Okay, so you locked, you wrote the primary site, and then after you wrote them, locked and wrote the primary site, you did a commit, but instead of doing the local commit and then propagating the values, you actually propagated the values and received an OK from the other side, and then committed. Of course, this will take longer to commit but it will be more beneficial if you have, again, issues with this, the system went down or anything like this, you make sure you propagated the values. But without any locking at all on the other sides. You just send the values and it says, okay, I received it. And that might happen several times and you still need to resolve it, okay? All right. So, replication issues. As you can see, we've seen several schemes of how to do that, several ways of achieving this. So the idea here is to, you want to make sure you achieve something we call mutual consistency. And this is again the consistency at the level of the data item that we've seen. But you also need to make sure we achieve transactional consistency. And that's the consistency we've been talking about earlier, which is the whole, we have multiple transactions and how things can work in a transactional kind of way. So the mutual consistency, we looked at the very simple, the very small operation on the very tiny data item, and even how to do the commit of this operation. Okay? So this is basically how we looked at this mutual. Transactional consistency, given a replicated scheme, how can you achieve a serializable schedule? Also, based on what we've seen so far, we've got an idea of how updates are propagated into the system. We've seen sometimes that updates can be propagated in an eager manner, eager update propagation, or lazy manner. Lazy means that you wait. You don't update the replicas all the time. You wait a little bit. You do a little lazy manner. So these are different schemes, and next time, okay, we will talk about these schemes in more details also. Okay. I was just gonna leave the last 2 minutes. Is it 2 minutes or? Okay, it's for you to ask about the project, but apparently you don't have any questions. So, yeah. I got questions about the midterm exam. Okay? The midterm exam will be a week after fall break. Okay? Not right after fall break, the week after. So you come from fall break, you relax a little bit, and then the next week there's an exam. Thank you.